Welcome back to Computer Lessons.
We have built a machine that can think with the CPU, remember the present with RAM, and paint beautiful worlds with the GPU. But there is a major flaw in our design so far. Our computer has amnesia. The moment you pull the plug, the RAM goes blank, and every thought, every document, and every game save vanishes instantly. To make this machine truly useful, we need a way to freeze time. We need a vault that keeps our data safe, even when the electricity dies. Today, we enter the arena of storage wars. We are going to explore the physical battle between the spinning mechanical ancestors and the lightning-fast silicon chips of the future. Let's start with the veteran of the industry, the hard disk drive, or HDD. If you open one up, it looks remarkably like a futuristic record player. Inside, there are shiny circular platters made of glass or aluminum, coated in a thin layer of magnetic material. When you turn on your PC, these platters spin at incredible speeds, usually 5,400 or 7,200 revolutions per minute. Hovering above these spinning disks is a mechanical arm with a tiny read-write head at the tip. This is a marvel of engineering. The head does not touch the disk. It flies over the surface on a cushion of air separated by a gap smaller than a single strand of human DNA. If it touches the disk, it causes a head crash, destroying your data physically. To write data, the head uses a tiny electromagnet to flip the magnetic polarity of a microscopic grain on the disk. North is a 1, south is a 0. To read data, the head detects these magnetic fields as they fly by. It is a completely mechanical process, relying on aerodynamics and magnetism. Because it is mechanical, it has physical limitations. To find a file, the arm has to physically move to the correct track, and the disk has to spin around to the correct sector. This creates latency. In the world of nanosecond computing, waiting milliseconds for a disk to spin is like waiting weeks for a letter to arrive. We needed something faster. Enter the SSD, or solid-state drive. The name solid state literally means there are no moving parts. No spinning disks, no moving arms, just pure silicon. Instead of magnetism, SSDs use a type of memory called NAND flash. Imagine a massive city of billions of tiny jail cells, which we call floating gate transistors. To store a bit of data, we shove electrons into one of these cells. Through a quantum physics phenomenon called tunneling, we trap the electrons inside a gate where they cannot escape, even without power. An empty cell represents a 1, and a cell full of trapped electrons represents a 0. When you save a file, you are essentially herding billions of electrons into their assigned cages. Because we don't have to wait for a mechanical arm to move, data access is nearly instant. An SSD can access data hundreds of times faster than a traditional hard drive. But there is a catch. The walls of these electron jail cells degrade over time. Every time you write data, you slightly damage the insulator. This means SSDs have a limited lifespan. Eventually, the cells wear out and become read-only. However, for modern drives, this takes many years of heavy use. For a long time, even SSDs were held back by their connection cables. We were using SATA cables, which were designed for the slow, mechanical hard drives. It was like driving a Ferrari in a school zone. The drive was fast, but the road was too narrow. We needed a new highway. Enter NVMe, which stands for Non-Volatile Memory Express. This isn't a new type of storage, it is a new protocol, a new language. Instead of using the old SATA cables, NVMe drives plug directly into the PCIe lanes on the motherboard. Remember the lanes we talked about for the graphics card? This gives the storage direct, high-speed access to the CPU. While a SATA SSD might move 500 megabytes per second, a modern NVMe Gen 5 drive can blast past 10,000 megabytes per second. This technology also brought us the M2 form factor. Gone are the brick-sized drives. An M2 drive looks like a small stick of gum. It lies flat against the motherboard, requiring no power cables and no data cables. It is elegant, efficient, and incredibly fast. So, is the mechanical hard drive dead? Surprisingly, no. While they are slow, they are incredibly cheap to manufacture. If you need to store 20 terabytes of security camera footage or back up the entire internet, you use hard drives. The cost per gigabyte is still unbeatable. Most smart PC builders use a hybrid approach. They use a fast NVMe drive for Windows and games, and a large, cheap mechanical drive for storing photos and videos. Here is a final thought on data security. When you click delete on a file, your computer doesn't actually wipe the zeros and ones. It simply goes to the file system, the index card we talked about in the OS video, and removes the entry. It marks that space as available. The data is still sitting there, ghost-like, until another file overwrites it. This is why police can recover deleted evidence, and why you should securely wipe a drive before selling it. We have now completed the core logic of the machine. We have the brain, CPU, the short-term memory, RAM, the talent, GPU, and the long-term memory, storage. We understand how it thinks, how it draws, and how it remembers. But all of this silicon is lifeless without one crucial element. It needs a heartbeat. It needs blood. Without clean, stable electricity, these components are just expensive rocks. In the next video, we will explore the most dangerous component in your PC, the power supply unit. We will learn why a bad PSU can act like a bomb inside your case.
Don't let your knowledge be volatile like RAM. Tell me in the comments, do you still have a spinning hard drive in your PC, or have you gone fully solid state? If you found this explanation helpful, please hit the like button and subscribe to Computer Lessons. Don't forget to click the bell icon so you don't miss our next class. Thanks for watching, and keep learning.